Welcome. In this video, we are going to explain the implementation of a two-pass assembler for an SIC machine. In this video, we will cover the following topics. What is an SIC machine? What is an assembler? How object coding is done? And its implementation using Python. Before going into the implementational details, we should know what is an SIC machine. An SIC machine is a hypothetical machine which has a simple machine architecture that is clear to learn system programming. In SIC machine architecture, memory consists of words of 3 bytes, where 1 byte is equals to 8 bits. There are 5 registers and each of them is 24 bits in length, that is 3 bytes. Now, in order to design an assembler, we should know what an assembler is and what it does. An assembler is a program that translates symbolic code into an executable object code. Now a two-pass assembler performs the above action in 2 passes. In the first pass, it assigns addresses to all statements in the assembly program. Also, it saves the addresses assigned to labels for reference in pass 2. In the second pass, it assembles instructions, generates data values, and writes the object program. In order to have a better understanding of how the two-pass assembler works, we should know how object coding is done manually for an assembly program of SIC. And here's a brief description.
First of all, we have an assembly language program of this format. First instruction is always assigned the address next to the mnemonic start. In the first pass, addresses are assigned to each instruction, keeping in mind the number of bytes it will take. Also, a table containing the labels and their corresponding addresses is created. Now, let's see how we can implement this using Python. The program takes an assembly language file as input and generates a file which contains addresses and object codes corresponding to each instruction. For the first pass, we create 2 files, acode.txt for storing the assembly code with corresponding addresses, and the other, simtab.txt for storing labels with their addresses. The first step is to extract the operand of start and store the corresponding address. For ease of calculation, we will perform decimal addition and convert the value to hexadecimal and store it. We assign the address and then calculate the number of bytes the instruction will take. For this, we are using a function cal_bytes. When the mnemonics are RESW, RESB, word or byte, the number of bytes to be allocated have to be calculated differently, such as 3 bytes for word. For all other mnemonics, we can search the file opcode.txt, which stores the information of each mnemonic with its size and opcode. Now, after we have calculated the address, we have to write it into 2 files. The first file is simtab.txt. It will store the labels with their addresses for reference in the second pass. It will look something like. The second file will contain addresses along with each instruction, and it will look something like. With this, the first pass is over. In the second pass, object coding is done. Each mnemonic is replaced with its opcode and the address of its operand or value. Let's look at the implementation. Now, for the second pass, we will use the previously created files simtab.txt and acode.txt. We will open them in the read mode. This time we will create the final file which will contain both address and object code corresponding to each instruction. So now we need to generate the object code for each instruction. The object coding is different for certain mnemonics like byte and word, where the object code contains only the value stored. Also, in the case of R sub, there is no operand, so we need to handle that case separately. For all other mnemonics, we follow a simple procedure. We find the opcode of the mnemonic using the file opcode.txt and find the address using the previously created symtab.txt. We combine the opcode and address and write it into a final file. Also, some additional operations have to be carried out where we use the X register, that is, the index register. After all these calculations, our result is stored in the file objcode.txt, and we also display the contents of the file on the screen.
Now, let's run the code and see the output it produces in various cases. First of all, we try to run the code for the assembly program code2.asm. It runs successfully and object code is generated correctly. The file which contains the final result is objcode.txt. Now, let's try to run the code for the file code3.asm. In this file, the mnemonic on line 6, KLT, is invalid. That is, this instruction is not defined in the SIC machine and therefore not in opcode.txt. When we run it, it generates an error. Now, let's look at code4.asm. Here, we have declared loop twice. When we run the program for code4.asm, it generates an error of multiple declaration. Now, let's look at code5.asm. In this file, we are trying to use the address of a label that has not been defined, that is XYZ. When we try and run the code 5.asm, we see an error again. Lastly, let's look at code 1.asm. It is syntactically correct. When we run code 1.asm, the program works correctly.
So in this video, we described what is an SIC machine, what is a 2-pass assembler, and how to implement it using Python. Hope you liked our video and do subscribe.